Riemann sums than my last curriculum did, which is good because I always felt like that was a weak point, which is why I sometimes feel like I'm a little weaker with it because it didn't talk about much. But okay, lesson 2 is summation notation, and officially it says writing area as a limit. So we're going to be working more with Riemann sums, but this is a matter of how to write them as a limit. Back in lesson 1 at some point, there was a definition, it showed an integral, and it showed it equal to a fancy limit of a sum. Okay, we're going to work on how do we write that fancy limit of a sum, which, as I said, that's a part that I feel like my last curriculum didn't really address much. And so I felt like it was kind of something that was just kind of, we don't know, you know. Here we're going to learn a little bit more about it. But okay, summation notation. And I don't know how much you guys are familiar with summation notation because it doesn't really come up in Algebra 2 or Pre-Calc much. And I'm not sure you would have seen it much before me. So one of the first things we're going to do is talk about what this all means here. But summation notation, or sigma notation, because there is a sigma there, right? Do we know our letters? Gives us a compact way to write Riemann sums into a single expression. This lesson will lay the foundation for the definition of the definite integral. While you may have seen sigma notation in an earlier course, we'll focus on using this tool to write Riemann sums. So, we're going to start with the basics here. Summation notation is a method for summing up a finite number of terms in a sequence, where the Greek letter sigma is the operator that indicates this process. This sigma means sum. It means to find the sum of a sequence of terms. Okay? Now, as opposed to writing it all out and saying, okay, we're going to find the sum of 1 plus 3 plus 5 plus 7, it's more the idea of it has a formula. Okay? So, when you see that sigma, backwards funky E, whatever, that's your summation notation. Okay? K equals 1 to n. Whatever's on bottom is your lower limit, so that's where we start. So we would start by plugging in 1. Upper limit is where you stop. So in this case, there is no upper limit. But like if this was K equals 1 to 5, you would start by plugging in 1. Then you plug in 2. Then you plug in 3, then 4, then 5, and then you add all those pieces. So this is telling us what to do. K, our index of summation, kind of the variable we use. And then x of k, that is the formula, the expression we're looking at. Okay? Now, what's really going to make sense is, okay, how do we do this? This is actually very easy, as long as you understand what it means. Have you guys done much with summation?
I think we saw it last year. Did we not see it last year?
It was like Algebra 2.
It came up somewhere? Okay. Okay, well, at least maybe it's not totally brand new then. So this says the sum from k equals 1 to 4 of 3k minus 2. We're going to do this by hand because we need to know how to do this by hand. But unbeknownst to me, my calculator can do it. I found out last night. Not right now. Oh, you've already done it, haven't you? Okay, so what does this say? From k equals 1 to 4, 3k minus 2. So we're going to start by plugging in 1. Then we're going to plug in 2. Then we're going to plug in 3. Then we're going to plug in 4. And then what do we do with all those terms? We add them all up. That's the idea. And yes, we're doing this one by hand. Okay, so I'm going to say, okay, my first one is 3 times 1 minus 2. Plus, then I'm going to do 3 times 2 minus 2. Plus, I'm going to do 3 times 3 minus 2. Plus, and then I'm going to do 3 times 4 minus 2. Why am I stopping at 4? Because my upper limit is 4. So what do we end up with? Don't look at mine, don't look at mine. There we go. Did you get it? Had math issues along the way, sorry. Okay, so the idea here that you are going 1, 2, 3, 4. When it says k equal, when it is an n on top, that means it goes on infinitely. Okay, so not something we can easily find by hand. But that's what we'll see with our limits. We're good? Okay. Example 2. Consider the sum 9 plus 25 plus 49 plus 81. Choose all answers that apply. So there are 4 choices. It's not multiple choice in the sense of pick the one that's right. It's pick any and all that apply. So there could very possibly be more than one. So I don't have a better way other than put them in and start seeing what happens. No, we're not going to use cap there yet. Okay, so in other words, this one is from 1 to 3. Huh, I just thought of something. When I did this on my own, I worked it out. But technically, I don't even have to work it out. How do I know right offhand A does not work?
There's no 4 terms.
Yeah, I need 1, 2, 3, 4 terms. 1 to 3 is 3 terms. I didn't catch that. Okay, so right there, I know A doesn't work because that's only going to be, since it's 1 to 3, that's going to be 3 terms. So if you catch that, that's good. Otherwise, what I did is I plugged in 1 squared, plus 1 plus 7 is 9. Then I plugged in 2. 2 squared is 4, plus 2 is 6, plus 7 is 13. That right there was my red flag because the second term was supposed to be 25. So either way, you get a no-go. Okay, you want to go over to B? Could be work based on the number of terms. How many numbers is 0 to 3? 0, 1, 2, 3. Count on my fingers, right? Okay, so at that point then, my suggestion is just start plugging in numbers, see if it works. When I plug in 0, we get 3, 3 squared, we get 9. Okay, first one's good. Plug in 1. 2 plus 3 is 5. 5 squared, 25. So far, so good. Plug in 2. 7 squared, 49. And plug in 3. 2 times 3 is 6. Plus 3 is 9. Squared is 81. Okay, what do we know? B appears to work, doesn't it? Okay. Try C. Does C work? Have you guys worked ahead? No? Let's see. If I plug in 1, 2, 3, 9 is good. Plug in 2, 25. Plug in 3. That's 6 plus 1 is 7 squared, 49. Does 4 work? 8 plus 1, 9 squared, 81. C also works. What about D? 2 times 1 is 2. Minus 1 is 1. 1 squared is 1. Okay. Again, just trying to make sure you're familiar with sigma notation. This is important. Okay. Okay. It is acceptable to use any letter for the index of summation. Most textbooks will use I, K, or N. You're going to see a lot of K's in this lesson. Okay. Be aware that some summation expressions may have other variables. For example, this is a summation from K equals 1 to 4, and it's 2 to the K, and then it's X to the 2K minus 1. We don't have a definition of what X is, do we? And so that's just a situation where your summation is going to have X's in it because we're just plugging our value into K. Okay? Now, as we do this, this is leading into Riemann sums, and this is leading into the limit notation for Riemann sums. So, I's, K's, yeah, sum from I equals 1 to 4 of f of x sub I. Excuse me. So plugging that in, it'd be f of x sub 1, f of x sub 2, f of x sub 3, f of x sub 4. Again, that's more the notation. And the idea there is that they use x star, but that could be any value, an arbitrary value on the interval, okay, on the provided interval. Okay, so again, familiar with notation here. Okay, example 3. For the function y equals square root of x, which we have a lovely provided piece of the graph, draw rectangles forming a right-hand sum, 6 equal subdivisions, n equals 6, on the interval of 1 to 4, where the width of each rectangle is delta x. Which really, if you're doing, makes it pretty obvious, but what is my width of each interval going to be? One half? Because from 1 to 4 is a distance of 3 divided by 6 intervals, so each one is going to be 1/2. So write Riemann sum. So from 1 to 1.5 is an interval. Since it's right, what are we doing? We're putting our point on the right side, yes? So that's from 1.5 to 2. Your point's going to be at 2. Are you pros at drawing these now? Well, you probably didn't have to really draw a whole lot in homework, did you? A little bit on the first page, and then after that you didn't have to really draw. From 2 to 2.5, right hand, so my point's on the right there. Draw the rectangle to the left. 2.5 to 3, my point is at 3. Draw over. 3 to 3.5, my point is at 3.5 on the right side. 3.5 to 4, again my point is on the right. 4 to 4.5, and 4.5 to 5. Gosh darn it. I got a little rectangle happy, I guess. Glad you guys caught it. Did we all catch it, or is it just me that kept going too far? Hopefully you didn't follow me. Okay, 1 to 4. Did this work out to be 6 rectangles then? It did, since I erased my last 2, right? Okay. A little bit of information here to make sure that everybody told us n is 6. What's A? A is 1. B is 4. And delta x we found to be 1/2, right? That's all helpful information to know. Okay, we're going to try and go through the process here, and then I believe it's the next page that it kind of summarizes the process for us, which will be greatly helpful. So our goal is to find a general expression for the area of the kth rectangle. In other words, A of k. Because, again, this is a limit. It's a limit. If you recall from the first lesson, it's a limit that goes as it approaches infinity. So we're trying to make an exact answer here. Now, so we're going to be talking about the kth rectangle in B. And actually, do I have B on the next page? I do. Okay, so the height of each rectangle is the function value at the right endpoint of the rectangle, right? We've done right Riemann sums. So those points are at right, so we know we're going to use that. Denoted as x of k equals a times delta x, or plus delta x times k. Find the expression for the height of the kth rectangle. Okay, so with this in mind, okay, we're finding the height. Now, x of k. Do we know a? What is a? 1, I believe, plus delta x is 1/2 times k, which is the value we're leaving in there. Okay, so this expression is going to be for the height of the kth rectangle. Okay, so you can write it as 1 plus 1/2 k. You could write it as 1 plus 0.5 k. You can write it as 1 plus k over 2. You'll see me do a little bit of everything there. So there is our x of k. That'll be one of our steps. Okay. Next, we're going to write the area of the rectangle, noting that the area is going to be doing the width times the height. Well, width, we talked about width. What is width? Width is the delta x. How big is, or how large is each interval, right? And f of x sub k is your height. Okay, f of x sub k is your height because that is the function value at the right-hand interval. In this particular problem, what is f of x? F of x was square root of x, correct? That was provided. So, what is f of x sub k going to look like? Besides something kind of ugly. Okay. Some variation of square root of 1 plus 1/2 k. Looks like this is where I switched to maybe using some 0.5. So when we're writing our area here, our A of k, it's the width, which we already discussed the width as being 1/2 times the height, which is the square root of 1 plus 1/2 k. This is what you will be integrating in your Riemann sum, because this is the area. Okay. I also have it written in my notes using decimals. So you could say 0.5 times 1 plus 0.5 k. Either way. Okay. Finally, we're going to write the summation notation for this expression for values from k equals 1 to 4. So, summation notation. There's my fancy sigma, however you draw yours. As we put our limits here, k equals 1. How many intervals do we have? We have 6 intervals. So when we talk about this, this is not my a and b values, but we're going to have 6 intervals. So there are 6 rectangles you're finding the area of, right? So this is going to be k equals 1 to 6. What's the formula for the area of the rectangle? That 1/2 times the square root of 1 plus 1/2 k. That's your summation notation. That's finding the sum of those 6 rectangles. Because that was the formula for the area of the rectangle, k equals 1 to 6. Now, we could do this by hand. Plug in 1, 2, 3, 4, 5, 6. Or, actually, it doesn't even actually say to find it, but this is a good opportunity to learn how to use your calculator. Can you find summation on your calculator? As most things, it's in 2 places. You can find it in the math menu, and you can find it in one of your alpha menus. And it's really just kind of a simple plug and chug from there, so to speak. Let's see, I don't even remember. So if I go into math, where was it? I think it's down at option 0. Yeah, if you go into the math menu, it's option 0. It says summation. And I can go there. And it'll bring up a little alpha thingy, or a little sigma thingy there that you can fill in. Now, notice it pops up alpha, because I guess they're assuming you're not using x necessarily, which we don't usually here. So alpha, I can find my k, which is on my parentheses. K equals 1 up to 6. And then type in your equation. So 1/2 times the square root of 1 plus 1/2 k.
Where did you find K again?
K is above the left parenthesis. It's green above the left parenthesis. You have to have alpha.
Okay.
So it's not a second function, it's the alpha function, so to speak. And we get that. We're not going to do it by hand, so you don't have anything to compare against, but I promise it works out. So this is approximately 4.9115. And we found that in the math menu, number 0, or it's in your alpha F2 menu, where you can find a lot of miscellaneous stuff like that. While we're here, under or overestimate? Overestimate? Go back and look at the graph, right? Okay. Top of the next page summarizes this process. Okay. And then at the bottom of the page, I think we use the process, or in the next example. So the process, and I know I found myself referring to this quite a bit, because as I said, this was something that was a little bit, I knew some of these pieces, but I didn't have a good process. So I was kind of glad to see these notes and a good process of how to do this. So, okay. Find the width of each rectangle on the interval, a to b. So that's using your delta x is b minus a over n. That'll be your width. Find the right end point of each rectangle. So that is finding x of k. This is what I had to look back at most, I think, is, okay, what is x of k? I think eventually by the time I got done with the homework last night, I knew it. I had it in my brain. Now, if I sit down to do it again, is it still fresh there? I don't know. But, and so it's going to be your a value plus delta x value times k. To find the area of the kth rectangle, so this is what will go in your summation. It's going to be the width times the height, right? This is your width times your height. And that's what we just did on that last example. With a right Riemann sum, your values will go from 1 to n. Okay, that's with a right Riemann sum, because with a right Riemann sum, like the one we just did, you'll always be looking at the right rectangle. So you wouldn't start at 0, you'd start at 1. What was pointed out in the notes was that College Board, AP, will most often do right Riemann sums in a situation like this. Okay, so when you're trying to write out the Riemann sum notation and the limit notation, it will most often be a right Riemann sum. Okay, which is good because it's a little bit easier. So that's what this homework focuses on, is right. A left Riemann sum, instead of starting at 1, would start at 0. Now, if it starts at 0, it starts 1 lower. So instead of ending at n, it ends at n minus 1. Okay. Example 4 is technically a multiple choice question. However, they didn't really give us any room to work. I didn't realize it was multiple choice at first, but use the procedure above to write the expression that represents the approximation shown below. So, We have some colorful rectangles. We're trying to write our summation notation for that. With that in mind, let's try and use that process there, okay, or the procedure. So, and I'm just going to kind of squeeze my pieces in wherever I can find room. Delta x. Well, actually, let's talk about a couple of things. What are a and b? 1 and 4, because those are my intervals when looking at the graph, right? What is n? 6, because when I say what is n, I'm asking how many partitions, how many rectangles, right? So can you find delta x? I know, some familiar values, huh? So delta x is 1/2. Easy enough there, right? That was officially step 1. Step 2, we need to know what x of k is. And so x of k, which is what I'm going to plug into whatever the function is going to be a plus delta x times k. So my x of k value is going to be a, which is 1, plus delta x is 1/2 times k. So there's my x of k value. Okay, here's the challenging part on this one. Forgot about this one. Officially, in order to find the area, we have to do the width, which we have the width, times the height. What did they not provide us with here?
The equation.
The equation. Okay, so with that in mind, it's what it comes down to is it's an equation that they're probably, I don't know. When I looked at her notes, the argument's going to be that it's an equation we should know. Now, okay, think about this graph. What do you see happening with this graph? If it's going up here, it's going out there. Are there certain places it's not crossing? Yeah. So right here, if you look here, it looks like there's probably an asymptote at 3. Now, what that is this is a certain graph moved up 3. And we only see the first quadrant. Do you guys remember the reciprocal graph? Reciprocal function? Reciprocal function is, back in pre-calc, it was, which way am I? I'm backwards from you guys, so I can never think about which way, but it's the two curves going out from each other, right? What's the basic equation for that? Do we know? 1/x, right? Now, here's the deal. This isn't quite 1/x, though. We have to adjust that top number a little bit. And notice the fact that a 1/x graph would be down along the x and y axis, right? So this graph is moved up. It's moved up 3. And so this is kind of side notes for a moment. This is not the final answer, so you don't necessarily have to write this down if you don't want to or figure it out. But this doesn't quite work. Because if we pick, where's a good point we can pick? For instance, if we pick 1, what is that, 1/5? Does this work for 1/5? Not quite. What could I adjust to make it happen? What could I change that 1 to? 2. And so the equation we actually need is 2/x plus 3. And here's the deal. When we've graphed those. We've looked at them back in Algebra 2 even as far. But that number on top just talks about how close it is to the center of the graph, right? So the bigger that number is, the more it pulls away. So like my centering point being right there, it pulls away a little bit more, Okay, so the function we're going to use is 2 over x plus 3. We can test this by plugging in some points we know. For instance, the 1, 5, right? It looks like maybe 1/2 comma 7 would work. Okay, so there's some things you could test. I don't know. I don't feel like that's an equation you'd have to necessarily be able to come up with, but it doesn't hurt to talk about it. So if we are using the function f of x equals 1 over x plus, not 1 over x, what's that supposed to be? 2 over x plus 3. What is f of x sub k look like? F of x sub k is going to be 2 over, what was x of k? 1 plus 0.5k. 2 over 1 plus 0.5k, and then plus 3. Well, good news is this starting to look like some of my equations here? It is. Okay. So, I don't even necessarily have to write it out at this point, but we could. Which one's matching up? Well, I guess I probably should talk about the fact that, what do we need to do here? We need to talk about this form right here. Yes, it's f of x sub k times delta x. And then we have to pick the right k values. So right here, I can already eliminate 2 of these. You see I can eliminate a and b? And I'm going to argue I can eliminate a and b because they're missing their delta x. Down here, these both have delta x. They both have the f of x sub k, right? So they both have f of x sub k times delta x. What type of sum is this? Is this a left or a right Riemann sum? These points are on the right corners, aren't they? So this is a right Riemann sum, which is going to lead us to C or D? C, because it's the one that goes from 1 to 6. Okay. The 0 to 5 would be if it was a left Riemann sum. Yes?
How do we get the 2 over x?
So 2 over x, I just thought of something. Since this is multiple choice, we could have looked at this over here. I should have led you as a different one. Okay. I just thought about this as an after fact. I kind of led us through it with, okay, and then let's pick the answer at the end. But if you looked at this right here, you can see that there's 2 over something plus 3. And once you find that that 1 plus 1/2 k is there. But anyways, what I looked at is trying to get you guys to recognize this as a reciprocal graph. Okay? If we can recognize this as a reciprocal graph, obviously it's not going to come all the way down to the x-axis. It's scooted up. And so that scooted up is your plus 3. A typical reciprocal function is 1 over x. But when I use 1 over x here, it doesn't match up when I start checking. Okay? So when I use 1 over x, it doesn't work. And so then it's a matter of, okay, I can clearly see that 1, 5 is a point on my curve. What's the tweak I can do to make it work? And it's tweaking that number there. The 2 is what? When I plug that in, 2 over 1 is 2, plus 3 is 5, and that's what works. As I said, I should have used the fact that this was multiple choice, and I should have used this as the idea that when these are all like this, shoulda, woulda, coulda. Right here, as soon as you see that that is our x of k value, the rest of this is my equation. Okay, sorry, afterthought. Problem with first time teaching it through. But that should have been my, oh, this is going to be 2 over x plus 3. Yes?
I don't understand. Like the 6 part.
6 is so from 1 to 6 is 6 values, and we had 6 partitions, 6 rectangles. Because that's how many things are we summing? We would be summing 1 to 6 are the values to plug in, and that's 6 things representing the 6 rectangles.
Okay.
Okay? Kind of? A little bit? Got it? Okay.
So if this was left-handed, it would have been D.
Yes. Yes. And the idea with the left hand is even though it's not at 0, it's the idea that that's the 0 value, the beginning value, because it's at the beginning of the interval, so to speak. It's not that we're saying we're at 0, it's that it's the beginning of the interval. So it's kind of like time 0, so to speak. Okay? Okay, down at the bottom, just a little bit of information there. A definite integral represents the area under the curve. I've already mentioned that. I don't know if it's stuck in your head a little bit, but definite integral represents area under the curve. We'll talk about that a lot. And a Riemann sum gives us an approximation of that area. Okay, so definite integral would give you the exact. We're just getting an approximation with these Riemann sums. We've looked. Those rectangles are obviously estimations, right? They aren't lining up exactly. Imagine that we could create an infinite number of partitions, or in other words, an infinite number of rectangles in a Riemann sum. Then the approximation would get closer to the actual area as the subintervals in the Riemann sum increase. And that's where we're going right here, is that the limit as n approaches infinity. As you get not 6 rectangles, not 20 rectangles, not 100, not 1,000, 1,000,000, as you're getting more and more rectangles, those rectangles are getting more and more precise, and it's getting to be a more exact answer. So I can't take a Riemann sum with infinite rectangles in our summation because infinity, there's not a number to plug in there. However, we can represent this with in subdivision. We can use limits, and that's what we're going to focus on the next page, maybe a little bit today, maybe tomorrow, not tomorrow, but so the exact value of the definite integral is the limit as n approaches infinity of the Riemann sum. And so here's your integral that we haven't done a whole lot with yet. That's coming, I promise. But it is equal to this limit, which is the Riemann sum. So because it's a limit, it will allow us to find the precise answer. Now, I did some research, and I cannot find a way. Yes, we can do integrals on our calculator. That's a requirement of a calculator that you use on the AP test. I have not been able to find a way on my calculator to do the limit of a sum, because I have not been able to find a way on my calculator to do a limit of something like that. I mean, yes, we can look at graphs, we can look at tables of values, but I haven't been able to find that. I will say the Inspire, I found out, can, but I don't think our calculators do. But again, I don't think that's a necessity for what we're doing. Okay. Okay. Where are we at? I'm trying to think. I start talking about this page, but I'm not sure I don't know if we can really get into that example 5. So this is probably where we will pick up Monday. So the definition is up there. Definite integral of a continuous function over the interval a to b. You keep seeing that. You don't probably understand it a lot or know a lot about it, but the integral from a to b of f of x dx is the limit of a Riemann sum as the number of subdivisions approaches infinity. So what you just saw on the other page. Area is this integral. It's also this limit, where x of k and delta x are defined. So the example, where are we at time-wise? I don't think I want to get into this. We have a graph, we have the interval. The exact area can be represented using this definite integral notation. Write the definite integral as a right Riemann sum. I think we'd be better off to talk about this on Monday because I can try and start it now, but yeah, we're not going to get very far. So we'll talk about it on Monday. I will, here, something to do in the last couple minutes. Play around with math menu number 9 on your calculator. And in fact, if you want to, you can fill in this blank by playing around with math number 9 on your calculator. and we'll talk about on Monday. But